Okay, so we are looking at the inversions problem under the divide and conquer strategy. So we'll see one more application of divide and conquer and then we'll move on. Okay, so this is the problem of finding the maximum integer in an array, which is a pretty straightforward problem. If you do it in the iterative fashion, you should have done in your 118 class. And we've seen that strategy also a couple of times in this course. So strategies usually pick the first element as the temporary minimum and or temporary maximum. I think here I want to find the maximum. Okay, so first pick the first integer as the temporary maximum and then go through the rest of the array. If you come across something else that is greater than what you think as the temporary maximum, update that to be the maximum and move on. So by the time you reach the end of the array, you should have found the overall maximum. Now that's an iterative approach of just going through the array in a loop. Now the time complexity of that would be n minus 1 comparisons. We saw that in the first module, and that would be theta of n. So that's the theoretical time complexity. Now what we want to do here is in the recursive fashion using the divide and conquer strategy, and we'll also see the time complexity is theta of n. So I plan to assign a programming assignment, I know, comparing iteration versus recursion, and this is a good example for that. So even though the theoretical complexity is theta of n for both, we know from the factorial problem that recursion is typically a time consuming approach because you have to keep things in a stack and then wait for the function to return back the value for the lower value. You call the recursive function repeatedly by passing the lower value as the argument, right? So in factorial, if you want to find factorial of n, you call factorial of n minus 1 and wait for that function to return the factorial value, and then you multiply that with n to get factorial of n. Similarly, you will see here, we will call a function repeatedly in a recursive fashion. So in real world, when you run a recursive program, it's expected to take more time compared to an iterative approach, and that's what you will evaluate in an assignment, which I'm planning to give you as a third assignment. Okay, so this will be useful for that. Okay, so let us go through the pseudocode and example and see how to do this. So let us say we have an array of 10 elements, 0 through 9 index. So what we'll do is we'll divide that into two sub-arrays, sub-halves. But you can see, unlike the merge sort, you don't really need to copy the array into two separate memory locations B and C. So you will see the space complexity of this for this problem under the divide and conquer strategy is theta of 1. We don't need any additional space. And let us use pseudocode to see why it is. So what I want to find here is, given array A, I want to find the index where the maximum element is. So in this example, the index where the maximum element is 5. There's another here at 60, the maximum is also here at index 9. So you could return one of them, and we'll see what this algorithm returns. You could break the tie in any order. We'll return the earlier occurring index as the index where the maximum is. Okay, let us see how it does that. So you pass to this algorithm initially the range of the index within which you want to find the maximum. So this code is very generic. So for example, you could pass the left index as 0, right index as 9 as the argument. So that means you're finding the maximum across the entire array from all the way from the index 0 to index n minus 1. That is the right index. But you could in general call this algorithm to find the maximum within any specific range, say from left index 2 to 6 or 1 to 4. So you could call this within any range of index entries within which you want to find the maximum. So this is very general enough to handle such scenarios. Okay, so initially let us say you do on the entire array. So A is the array pointer, and then left index is 0, right index is n minus 1. So if left index equals right index, so that means you have called this recursive function by passing a subarray or a pointer to a subarray such that the left index is equal to right index, means there's only one element that you have to work on and find the maximum. So there's only one element to work on, that itself is a maximum. So we'll just say return left index. I could say return right index, but as I said, we'll break the tie in favor of the earlier occurring index, so we'll say return left index. So this is like a terminating condition for a recursion. Okay, so you will start with the entire array, keep breaking it into sub problems, and then we'll reach a point where the sub problem is of just size 1, and that is when the left index will be equal to the right index, and you can just return left index as the index where the maximum is for that subarray. Now, if the left index is not equal to right index, that means you have a subarray of size more than 1. Then you need to further break that into sub problems. So that is what we are going to do. That's the divide part. You are going to first find the middle index around which we'll break that problem into that array into 2 subarrays. So we'll find the middle index as the average of left and right index. So in this case, we're working with 0 and 9. The middle index will be 0 plus 9 over 2, which is 4. So then what we'll do is from the left index, which is 0, all the way to the middle index, that's one subarray, and then from middle index plus 1 to the right index, that's another subarray. So I'm going to call the findMaxIndex recursively by passing the array, the same array pointer. So you're still working on the input array, you're not creating any separate copies of that input array, you're still working on it. Just passing the pointer so that you can keep track, you can access it from any recursive function. So you pass only the index, the left index to the middle index. That's one sub problem. So what, as I said, is by calling this recursive function like this, you are trying to find what is the index where the maximum element is within this left index to middle index. So basically you are trying to find the index of the maximum element within this range from left index to middle index. Similarly, you want to find the index where the maximum element is within this index starting from middle index plus 1 to right index. So that's what we are doing here. So let us call that index where the maximum element is within this range of left to middle as left max index. And then let us call the return value of this function. So this function returns the index where the maximum element is within the left index to right index range. So when you call this within the middle index plus 1 to right index range, it returns the index where the maximum element is within this range. And let us call that as right max index. So in this example, among these elements, the maximum is 50, and that's at index 3. So that will be your left max index. And among these elements, the maximum is 60, and as you saw, we break the tie in favor of the left or earlier occurring index. So the right max index, that's the index of the maximum element is within this range, is 5. So those will be the values of left max index and right max index. That's the index entries where the maximum element is within that range. So once you get the solution, so these are the solutions of your 2 sub problems. So we divided the problem of a larger size from left index to right index to 2 sub problems ranging from left index to middle index. That's one sub problem, and you're trying to find the index where the maximum element is within that range. Similarly, the other sub problem from middle index plus 1 to right index. So you got the solutions of the 2 sub problems. Now you are trying to combine the solutions of the 2 sub problems and decide the solution for the larger problem. So that's the conquer part. So you divided into 2 sub problems, found the solutions of the 2 sub problems, and then you're trying to merge or combine the solutions of the 2 sub problems. So how do we combine that here? So we know for each of these ranges where the maximum element is. So you have to just compare the maximum in each of these 2 ranges. So when you say A of left max index, you are basically accessing that value where the maximum is within this left subarray. So left max index is 3 and the maximum and the data is 50, and right max index is 5 and the corresponding data is 60. So using the 2 index entries, you can access the corresponding data and compare and find out which one is greater. So the logic is, if A of left max index is greater than or equal to A of right max index. So if the element at left max index is greater than or equal to right max index, then the element at left max index is the greater of the two arrays, of the two sub arrays, right? So we return left max index as the index where the maximum limit is. So in case if they're equal, and you can see again we break the tie in favor of the left index. So that's why you have the greater than equal to sign here. Now else, that means A of left max index is less than A of right max index. So it means the element on the right side is the maximum. So we return the right max index as the index where the maximum element is for this entire range from left index to right index. So that's what we do recursively and find the overall maximum. So let us go through this example now and let us see how we find the index where the overall maximum is. So what I show in this slide is the divide part, and then we'll merge the solutions of the sub-problems. So you see the recursive call. So we start from 0 to 9 as left index to right index and divide that into two sub-problems. So this is your 0 to middle index and middle index plus 1 to right index. Now you call the findMaxIndex on this subarray ranging from left index 0 to, now this is our new right index 4. So once you divide, you see here, I start here and call findMaxIndex starting from left index to middle index. So that means you don't even have pass the control to the next statement. You just work on the first recursive call right away. So that means from here you right away go to this subarray, this subproblem. So on the same array you still work based on the index and the same array pointer, and now try to break this into two subproblems. So you will call again from 0 to 4, that findMaxIndex. So the middle index now will be 0 plus 4 over 2, which is 2. So you break that around index 2. So now 0 to 2 is one range and 3 to 4 is the other range. And now again work on finding the index of the maximum element is in that left subproblem. So within 0 to 2. So break that into 0 to 1 and then 2. And then you again work on the left sub problem. So you break that into 0, 1, 0 and 1. So if you try to what I call like in the merge sort problem, if I want to show you the sequence of recursive calls. So you start with this one. So let us say start with this. This is the first sub problem you're trying to find out, and then you're trying to break this into two sub problems, and then break this into two sub problems. That's the third recursive call, and then work on this sub problem, which is the fourth recursive call. So try to find the maximum within that one element array. So this is when the left index equals the right index, which is 0. So you will be returning the left index, which is 0, as the index where the maximum element is within this subarray. So but now in our what you see, so you got the left max index, which is that 0. Now you need to find the right max index to actually combine the solutions of the two subproblems. We got solution only for the left subproblem. We need to now find a solution for the right subproblem, which is in this case, what's the maximum for index of the maximum element is within this subproblem, which is going to be 1 itself. So that's the index, and we need to so that is the next recursive call. So you see, this is in a depth first strategy. So we saw depth first search in data structures. So that's the kind of order in which things were going on. So you try to find the maximum within this right subarray. That's going to be 1, and that's what you're returning as the right max index. So you got left max index and right max index, 0 and 1. So you try to combine the solutions of the two subproblems, find the maximum find A of left max index compared to A of right max index, and in this case left max index is 0, right max index is 1, the corresponding data are 30 and 40. So that means the maximum is on the right side. So we return 1, which is the right max index value, as the maximum within this range. So you got now the solution for this problem ranging from 0 to 1, and that is 1. So that will become the left max index for the parent node in the recursive tree. So this 1 is the left max index for the range from 0 to 1. So now we have to find the right max index with which you can combine that solution. So the right side sub-problem is just this one element array. So that is now the recursive function that is called. So you see how the recursion order in which the function is called is coming up. Okay, so you go all the way down deep and then kind of back up. So for this subarray, the index of the maximum element is 2. That's one element array. So that is the right max index. So now we are combining left and right max index. So left max index is 1, that is the data is 40. Right max index is 2, the data is 10. So the maximum of 40 and 10 is 40. So that will be the corresponding to A of left max index being greater than or equal to A of right max index. So you return left max index as the maximum. So that means you will be returning 1 as the maximum for this range. So this is now the parent node in the recursive tree ranging from 0 to 2. So this becomes now your left max index. So now you try to find the right max index in the right subproblem 3 to 4. So that will be now the next recursive call that is made. So that will be 3, that's the right max index you are returning. So now compare the values at these two, left max index and right max index. It's 40 compared with 50. So 50 is larger, so return right max index as the maximum for this entire range from 0 to 4. So now the left max index is determined. So now you need to find the right max index for the subproblem ranging from 5 to 9. So you go through the same set of recursive calls. So this will be now called here 8, and then again go all the way deep. So you now try to break this into two subarrays, 5 to 7 and 8 to 9. So you will be calling that to find the maximum first within this range from 5 to 7, and to do that you will break that into two subproblems. So you will solve for 5 to 6, and for that you need to solve for 5 and 6, combine the solutions and so on. So this is what I am showing here. So the maximum now is 50, between 50 and 23. So you return 3 as the index, as the maximum within this range from 3 to 4. So I'll explain this. Now this one, 60 and 12. So 60 is the maximum, so return 5 as the maximum from 5 to 6. Then 33 is a one element array, so 7 is the right max index. So 60 and 33, 60 is greater, so 5 is the index you return from this range 5 to 7. On the right side you get 9 as the maximum index where the maximum element is. So now compare the elements at index 5 and 9, it is 60 and 60. So that is where A of left max index is equal to A of right max index, and you will return left max index. So that means you will return 5 as the maximum. So you got left max index as 3, right max index as 5, and the data is 50 and 60 is greater. So return the right max index, which is 5, as the overall maximum in the range 0 to 9. So you see that we have accomplished this using the input array itself. So we don't need any additional space corresponding that's proportional to the input size. Of course, we use the temporary variables for left max index, right index, and so on. So, but these are not going to increase as the array size increases. So it's going to still remain the same number of temporary variables. So the space complexity of this approach is state of 1. Now let us do the time complexity. This is recursive based, so you can use the recurrence relation. So to sort a problem or to find the maximum in a problem of size n, you're breaking into two sub problems of size n over 2, and you're trying to find the maximum in each of those two sub-problems. So which means you're trying to solve both the sub-problems. So that's why for one sub-problem the time is t of n over 2. So the two sub-problems, so it is 2 times t of n over 2. Now what's the time to combine the solutions of the two sub-problems? So you got the two solutions of the two sub-problems, which are your left max index and right max index. So this is the combining part of the solutions. So in the combining part, you are just comparing the values of the elements at the left max index and right max index. So it's just one comparison that we are doing. So that can be indicated as 1 here, the number of comparisons. That's a kind of basic operation. So we can write this 1 as theta of n raised to 0. So why I write like this? Because we want to solve this recurrence now using master theorem. Okay. And again, this recurrence, even though I did not mention it here, this is true for n greater than 1. Now for n equal to 1, we are not doing any comparison. So an element by itself is the maximum. Okay. Alright, so now to apply master theorem, we have to identify the a, b and d values. So the general format is a times t of n over b plus theta of n raised to d. So a is 2, b is 2, d is 0. So the next step is to find b raised to d, which is 2 raised to 0, that is 1, and then compare a with b raised to d. So here a is 2, b raised to d is 1, so 2 is greater than 1, which means a is greater than b raised to d. So we saw 3 formulas for master theorem. If a is greater than b raised to d, the formula is t of n is theta of n raised to log a to the base b. So you can use that formula here, and that would lead to theta of n raised to log a is 2, b is also 2, so 2 to the base 2. So log 2 to the base 2 is 1, so that means theta of n raised to 1. So that's why you see here, in theory, the time complexity of the divide and conquer, which is the recursive approach, is also theta of n, and the iterative approach would also be theta of n time theoretically. But there's an overhead that comes with recursion. As you call these functions recursively, there's a lot of overhead in memory, and then also you have to wait for the after you find left max index, you have to wait for the right max index to be determined, and then only you can combine the solutions. So that's the waiting time. So, and the operating system can schedule these function calls to be executed at different times. They need not be executed sequentially. Okay, so it may find the left max index by calling this function recursively, and then it may run some other program in your computer. It may not right away call findMaxIndex and find the right max index. So once it calls the other program, it will wait for the result of that program to get completed, and then it will call the findMaxIndex to find the right max index for the right subarray. So that means there's some waiting time. There could be some waiting time involved between two recursive calls. So that will all add up to the time complexity in real world when you find it. They are not kind of being captured when you do the theoretical time complexity. Okay, so that's the difference between analyzing the time complexity of algorithm theoretically and in real time. So in theoretical analysis, those waiting time by the operating system are not captured, and that could make a difference in real time. Especially if you are working on a larger subarray, you can think about there will be a lot of recursive calls. The recursive tree will be so deep, and you will have to wait for the recursive functions to be executed. So that's why recursion is not a good strategy. It's not the first approach that you should try. If iteration is possible, iterative approach is possible, you should go for that compared to the recursion. Right. So any question on this? This is another good example to compare recursion and iteration.
I have a quick question.
Yes.
So when we're splitting the array into subarrays, I noticed that it's split into at during the second recursion. You can go back to
This one?
During the second, yeah, this slide, the second recursion, it splits into 3 and 2. How does that work if we're like doing like n over 2?
So you mean this
Like,
one splits into 3 and 2?
yeah, yeah.
Yeah, so that depends because the larger problem is of size 5 elements as an odd number. So if you want to split that into two sub-problems, there's no alternative. You have to split that into two sub-problems of not the same size, so something of size 1 less than the other one. But that doesn't really has to do anything with the overall time complexity. Overall, this is how you have to look at it. You're dividing a problem of size n into two sub-problems of size n over 2. And again, you're looking at the asymptotic time complexity. So as n increases, the difference of 1 in the array size in the two sub-problems does not really make a difference. So this is the reconciliation you have to solve. So in each case, this is what you're doing. You're breaking the problem of size n into two sub-problems of size n over 2. That's how you have to look at it. Is that clear?
Yeah, that sounds good.
Okay. Alright, any other question? So let me save this.